as this last time, which probably made it very exciting for you to figure out what in the world's going on. So we're going to have hypothesis testing on the exam. Yes, chapter 18 will be on the exam. Chapter 19 will not be on the exam, although we'll cover it today. So here is a bunch of information from last time, but what I'm going to try and do is go ahead and spell it out a little bit clearer for you on the next slide, okay? So I'm just going to go ahead and advance it, and again, you can, we'll just kind of double check this in a second. Okay, so then with the hypotheses, we set that all up. That was no problem, I don't think, in this situation, because you had H naught such that the mean was equal to 6.1, HA such that the mean, I think, was less than 6.1. So that's no problem. The issue kind of came when we got into this, the calculations. Let me kind of talk that through here, okay? So the first thing you want to do is compute the so-called test statistic. And what I chose to do is spell this out a little more clearly and in a step-by-step format for you versus all the what you saw previously. So you have the test statistic, and we had negative 3.20. So yes, on a formula, or yes, in the exam, you will use a formula to compute that, and get negative 3.20. The next piece is find the p-value. So on the t-distribution chart, you have some values. You go down to the row with the appropriate degrees of freedom, and you saw a 3.03 and a 3.385. Okay, so with the T chart, what you want to do is, where is my test statistic on relative to this chart? So how far down do you want to go depends on the degrees of freedom. In this case, you want to go down to 36, 35 or so, but there was no 35 rows to go down to the smaller one, which is just round down to 30. We have a 3.20, again, look at the absolute value, so to speak, and the two values are 3.03 and 3.385. So 3.20 was in between 3.03 and 3.385. And again, this is for the t-distribution chart at 30 degrees of freedom. So go down to 30 and then go across to the closest thing to your test statistic, which is in between 3.03 and 3.385. And if we have time, I'll come back to this at the very end of class, and I'll show you the actual chart, and we'll look at it again. But some of you should have this in your notes. So then when you come down to that situation here, 3.03 and 3.385, what I would do on the exam, I would, in pencil, write down where my test statistic is relative to those two numbers. So I would even just write it on the chart, and do that on your homework too. And then that makes it simple, right? Because you come down here to the bottom, you have a one-sided test, and so 3.03 corresponds to a p-value of 0.0025, and 3.385 corresponds to a p-value of 0.001. And then you just use your mathematical reasoning, right? If one critical value gives you this as a p-value, and the other gives you 0.001 as a p-value, and my statistic is in between those, then guess what? My p-value is in between these two numbers. And so all of this is where I get that from. It didn't just come out of thin air, so to speak. Okay? So because 3.20 negative is between those two numbers, then of course its p-value is in between those two corresponding. Yes?
Where did you get the negative 3.03 and negative 3.385?
Ah, good question. So because the t distribution is symmetric, right?
Okay.
Our chart only gives us positive values, so then we can kind of assume that the negative ones will correspond accordingly. So the area bigger than a positive 3.03 is the same as the area less than a negative 3.03.
Okay.
Oh, no, I don't like that. Okay. All right, so here's 3.03 with some area of 0.0025, right?
Yeah.
If I flip it, then this guy's got to be 0.0025 by virtue of symmetry.
Yeah, I get that. I just mean from the negative 3.20, where did you get the negative 3.03 and the negative? Like, how did you pick those two numbers?
Ah, okay. So, so I use the T chart.
Oh,
Okay.
okay.
All right. So the T chart doesn't have the negative values, but you can still look at the positives and then assume the symmetry holds. Now, again, I know it's one of those okay, but would you like me to show the chart and how I got it from the chart? Would that be helpful? Okay, that's what I need. So I have no problem slowing down and making sure everybody has a better picture of how this goes. Okay, so give me a second. And again, my theory, some of you are like, well, why is she making us stop? Well, you know, my theory is that for every person who has a question, there's 5 or 10 already thinking like, yeah, where'd she get that question from? You know, so let's go ahead and talk about it. All right, so here's the chart, right? The T chart. Okay. Ah. It shows it in mine. That was. Okay, we're getting there. Voila. Okay, so the question is, where in the world does 3.03 come from, right? Okay, so let's check it out. So we had 35, I guess 36 or so was the sample size, but the closest thing was 30, which is here. And so you're going to go down to 30 degrees of freedom and find the closest thing to your test statistic, which was 3.20. Again, look up the positive value in this case because of symmetry. So I'm just going to walk along this chart until I get to 3.20. And what I would do, if I could write on this screen, I would put 3.20 right there. And it's in between those two numbers. Okay? So your test statistic may not fall exactly on this chart, but it's going to fall somewhere in between two values, or even bigger than some, but usually between two values, and then you have to find the probability from there. And then that's when I come down here. Yeah, got something. Okay. So then 3.20 is between these two numbers, therefore its probability is between these two numbers for a one-sided test. All right, so what are the steps? Find your test statistic, okay? First step. Second step, how far down do you go depends on your degrees of freedom, okay? Determine how far down to go on the chart. So test statistic, how far down to go, and then you're gonna walk over to closest number or two numbers that are to your test statistic. And then the fourth step is find the p-value. All right, so I'm going to go ahead and enumerate that. Yes?
We're comparing this at a 0.05 significance level. Why would you not just find the row with the degrees of freedom?
And go across to 0.05.
95.
Okay, so and someone else had a question about that on Tuesday, I think it was. So, if you wanted to find the what we call the critical value and determine if you're going to reject based upon the rejection region, then yes, you go down to 0.05 and say that that's going to be what somewhere in here, 1.697 or so, right? So that gives you that helps you decide to reject the null hypothesis or not reject the null hypothesis. So that's the question someone asked me earlier on Tuesday. However, if I wanted to ask you for the p-value, then you have to go ahead and go as close as possible to the corresponding critical values. Okay. So yes, his question is, why can't you just stop at 0.05 and make a decision? True, you could, but if I ask you for the p-value, now you got to get a little more precise. Okay. And this book does not emphasize rejection regions per se like other books. So they emphasize p-values, hence that's why I went a step over. Okay, so back to your question. Are we in a better spot now? Okay. Let it sink in. All right, so and I appreciate your courage in asking the question because I'm sure there are plenty of other folks who are thinking like, yeah, how did he get that? Okay, so we're good, more or less. All right, so the first thing we want to do, go ahead and pick this back up. Oh, it's going. Is, like I said before, you want to find the test statistic. You want to determine which row to use in the t-chart. You want to find the corresponding critical values and the p-value. So test statistic, how far down, how far over, and then get the probability at the very bottom of the chart. And again, you make the decision that the p-value is smaller than 0.05, so then you're going to reject the hypothesis. Yep. Okay, so then our conclusion if we reject the null hypothesis, then we have something like that. Okay. What I'm going to do is, so if you reject the hypothesis, then you're going to say you have sufficient evidence to make some kind of decision, and then go back to the very beginning question that was asked, right? The question dealt with, does Lucy have significantly less screen time than the average person? Her age. And so in this case, the answer is yes, we can kind of make that conclusion about our dear friend Lucy. Okay, so we're going to do another example with the hypothesis testing, and then you guys will walk me through that, and then we'll go into chapter 19, which will not be on the exam, but it will be on the final, so hang tight, right? Okay, so we had the so-called matched pairs procedure. Okay, and so for the most part, and again, I know you guys are working really hard to write down, fill in all the blanks and that sort of thing, so I'm trying to minimize that. But pretty much, we talked about matched pairs before, where you have similar subjects, okay? So you're kind of comparing, let's say you have twin boys, and you're kind of comparing their performance on some tests, right? So then they're very similar, so you got to make those, you know, boy 1 compared to boy 2. And then gender issues, male to female, that sort of thing. So we use those for matched pairs because they're similar in nature. But I like to use the pair t-test, so to speak, for before and after. Okay, so for example, you monitor some people's grades in the first half of the semester, and then they start going to tutoring, right? And then you monitor their grades in the second half of the semester. So you kind of can compare how effective tutoring was to their performance in the class. But it's the same people, so you just look at before and after. And then the before and the after creates one variable of the differences. All right, so then that's why I say here that you're going to pretty much compare two treatments on the same subjects. But here's the big thing: you're going to apply the one sample t procedures. Even though you have two variables, when you find the difference, you just have one variable, and then from there you can use the one sample t information that we use. All right, so then here's some very fictitious people: Amy, Bob, Cal, Dee, Eve, Faye, etc., etc., etc. Okay, and so here's this idea that music kind of calms you. Some of you guys study with music on, right? Some of you get into sports with music on to get yourself fired up, I guess. But here's this idea: if it calms you, then your blood pressure or your pulse rate should decrease. You should become less anxious, more or less, all right? So that's what that data set is doing here. And so then what I chose to do, and you guys can just fill this in below your data values, is look at the difference in the pulse rates. So Amy, after listening to some music, her pulse rate is 6 beats per minute lower. Bob, well, he got more anxious, I guess. It's one beat higher. But pretty much everybody else has witnessed a decrease in their pulse rates. Okay, so to be consistent, I tend to look at what I'm trying to prove. So if I'm trying to prove a lower pulse rate afterwards, then I'm going to look at your final minus your initial. So I'm thinking in this direction, right? if my final pulse rate is less than my initial, and the difference variable is final minus initial, then I'm going to say that this difference is going to be less than 0. Does that make sense? Okay. And again, if you want to use algebra, you just had this intermediate step, final minus initial is less than 0. So just bring the word initial, or the variable initial, to the left-hand side, and you have final minus initial is less than 0. And if you define difference as this quantity here, then I'm saying that that difference is less than 0. Again, just a little bit of algebra. It's 8 in the morning. Let it sink in. The only problem with that is you have to deal with these negative numbers. Oh, okay. We don't like negative numbers, right? So at the very end, I'm going to show you. Let's talk about this for a second. What would I do if I didn't like negative numbers? How could I rephrase this? Well, if I didn't like negative numbers, I could look at the initial minus the final, right? And then that would be 6, -1, -3, 7, 12, so on and so forth. Okay? But I'm just going to mention this briefly. Don't write this down per se. If I was interested in initial minus final, then that's going to be bigger than 0. Stay with me, right? But then my claim in this case would be that the difference is bigger than 0, more specifically that your pulse rate was higher before the intervention So again, I'll put this kind of like a dashed line, so to speak. There are two ways to think about it, right? I can look at the difference of final minus initial and say that my final is less than my initial. Or I can basically say that my initial is higher than my final. So the left-hand side is final minus initial. This side over here is initial minus final. Okay. Right. That's like saying this: 3 is less than 5, or you can say 5 is bigger than 3, depending on how you want it. It's the same kind of concept. So I'm going to focus on this side here because of what I'm trying to prove. So we'll say big old or right there. If you hate negatives, you can try it that way and just prove that the initial pulse rate is higher than your final pulse rate. But you guys can handle negatives, right? So let's keep it moving. Just like with anything, well, let's see here. You can look at a histogram, and this was on your review sheet if you took a chance to look at that. Okay, data is not necessarily purely normal, but for our purposes, it's pretty darn close. Okay, and I give you these summary statistics. So we're going to need this mean here of 7.5 of the negative, and we'll need this standard deviation also, and we'll probably need the sample size. Yes?
I don't know if you noticed, but the slide before with the data, the result of Gus is incorrect.
Oh, -3?
Yeah.
Oh.
I don't know if that would mess up with your graph or the histogram.
3 minus, let's see here. So that's just 3, right? Okay, so someone had a comment over here.
Yeah, Mo is positive 7, but negative 7.
Come on now. Yes, positive 7. Okay, so we gotta clean all that up. So that could throw things off a little bit. All right, so the show will go on. All right, so thank you for the points there. Okay, so then in this case, let's see here. We're gonna go ahead and go through the process. Okay, so the question is this: what is the practical question that requires a statistical test? State this verbally and mathematically. So the question is, does music reduce stress? Okay, and what I want you guys to do is kind of follow this template in moving through the actual data. Okay, the hypothesis test. So I'll double check that stuff. So the first thing you want to do is say, okay, what's the question we're trying to find out? In this case, does music reduce stress? That's going to be in the corner there. And then now we're going to look at the difference between the average pulse rate after relaxation program and the average initial pulse rate is less than 0. So that's basically saying this guy down here. The final average is less than my initial, or the difference, the variable that measures the difference in the two is less than 0. And I have a fix for that Mo and Gus issue that we talked about. And on the review sheet, I kind of scaffold and walk you through each of the little steps in between. Okay. And again, you could look at the difference between the initial pulse rate and the final pulse rate and conclude that that average is bigger. But again, if our goal is to show that it reduces stress, then I'm gonna look for less than. Because reduce and less than tend to align a little bit better than me flipping it back around. If you didn't get all this verbiage here, make sure you at least understand this component here. Okay, so then now, identify the parameter that we're working with, or we're looking at the average difference between the initial and final pulse rate. And then what's given? Well, we had a sample size of 12, a sample mean of 7.5, and a standard deviation of 7.657. Yes, negative 7.5. Okay. Make it a little bit clearer. There we go. Negative 7.5. Significance level is 0.05. Alpha equals 0.05. We have a left tail test. And then we have some critical value t such that it's going to be determining our rejection region. Of course, you go down to 0.05 in that case to get that value. This book doesn't really stress that, again, like I said before. All right, next piece. So check the conditions. Okay, there is a handout. Yes.
Question about the hypothesis, the null hypothesis.
Got it.
Could it be the mean of the final is equal to the mean of the initial?
Yes, it could be that. And let me write the HA in here too. Right, it could be that the mean for this, the variable that measures the difference is equal to 0, right? That there's no difference. And then yes, if there's no difference, then that means that the average before and the average after are the same, okay? The only issue with that expression is that implies two different variables, okay? Whereas we're looking at one. So I have one parameter here, whereas what you're talking about is two parameters. That's next chapter, actually. And we'll have like mu final equals mu initial. Okay, so there's the alternative two, that the average is less than 0, that the average is equal to 0 is a null. All right, so what are the conditions? Pretty much they will be satisfied for the most part. So is it random sample? Yes. Are there more than 12 students in the world? Yes. And we were told that it's pretty much normal. So these are the three key conditions that you have to think about as you do these problems.
It's always going to be a t-statistic. At
Um,
least
if
if it.
the standard deviation sigma is not given, then yes, t. I can't say any more right now. Okay, but yeah, if there's no sigma, then assume t. And in certain cases, when the conditions aren't met, there are other procedures beyond this course, but we will assume that we'll use t. All right, so when you find the test statistic, and this formula is given to you come next Tuesday, so you just go ahead and plug it in. The sample mean is negative 7.5 over the standard deviation divided by the square root of n, a negative 3.393. So again, this is where we want to use that t-chart to figure out where, in fact, this value falls. So according to the t-chart, I'm going to go down to 11. And of course, you'll be given the chart tomorrow or Tuesday also. So down to 11, and then over to the closest thing to 3.393, which is between
How did we get the
Okay, good question. This guy right here. Assume that they're equal.
That's the assumption.
Right. If we assume that they're equal, then there's zero difference. And then if there's zero difference, we plug that into the equation. Okay, go down to, let's see here, 11 and 3.393 is between 3.106 and 3.497. So 3.393 is between 3.497 and 3.106. So the p-value between those two numbers. And so the p-value between those two numbers then is less than 0.05, so we can reject the null hypothesis. So we reject the null hypothesis, and we conclude that okay, and again, the test that we did today was based upon the final minus the initial. Similarly, if we did initial minus final, we would have had a positive 7.5 for the mean, and then we'd say that, yes, you are more stressed before you have music, which is similar to saying that there's less stress after music. More stress before is the same thing as less stress afterwards. Okay, so here we go. Based upon our data, do match pairs lead to independent or dependent samples? Well, independent means that the variable from the the data from the second variable is not related to the first, or dependent is that they are related. And so we're going to say that it's dependent, okay, because it's the same people in the survey. All right. Next chapter, we're looking at independent samples, where you may have two totally different groups. But if it's the same person, typically people who had lower pulse rates in the first measurement had lower pulse rates the second time around, even lower actually after the music is concerned. So when you have dependent samples, you want to take the difference and then do a t-test for that. So in the same way that you had hypothesis testing and test of significance for one sample, you also have confidence intervals. So it says here the example is continued. Let's also construct a 95% confidence interval for the average difference in pulse rates. So you still have the same formula as before. The sample mean was a negative 7.5 plus or minus some t-score. Standard deviation is 7.657 over the square root of 12. Okay, so for the t-distribution, you want to go down to 11 and across to 95%. So that's 2.201. So when you say, hey, how did you get the 2.201? I went down to 11 and across to 0.95 or 95%. Okay, so this margin of error, when you do the math, turns out to be 4.865. And so then that's going to be the confidence interval. And notice here on both sides, they are both numbers less than 0. Oh, that makes sense because we're looking at the difference. And we're saying that the pulse rates will go down after you listen to some music. So that's the average amount of a decrease we're going to see in pulse rates. Yes?
Don't they already give you confidence interval? The start next to the graph?
Yes, but let me come back to that. Okay, let me come back to that.
I also had a question about when you're going through like the parameters.
Yes.
If it's or checking the conditions, like when you say it's large enough, like on a practice test, the answer was because it was between 15 and 40, it was big enough with no skews or no outliers. But on this one, you said because it's normal. So it's basically just asking, is it normal?
That's right. Yeah, because all of our procedures, look at even the graph there at the bottom, is that bell curve. So we're kind of making that assumption. Okay. It even says in chapter 18, if it's normal, you're good. If it's not normal, then look at the sample size. Okay. But back to your first issue, you said, oh, it's already printed off, right? Okay. So anyway, if it's not already printed off and provided for you, these are the steps you have to go through. Okay. So then we're going to say here, okay, so we're going to say that we're 95% confident the mean difference in pulse rates is between negative 2.635 and negative 12.365. Moreover, we're saying that the relaxation program reduces your pulse rate by 2.6 to 12.4 beats per minute. That's what that negative is. It's reducing it. And then, of course, That's the amount that's being reduced. All right, so we're not quite done yet. We're going to look at some technology output. So this is it Darren? Your name? Derek, okay. So Derek says, hey, Dr. Baker, you already gave me the answer. Well, good point, Derek. The point is, though, that you can do it manually by hand, or you can use jump and get the same results. So earlier, by hand, we had this guy as X bar. Jump has the same thing. The standard deviation, right there. The test statistic, we did this by hand. That was our T at negative 3.39. And look, you are hardly ever going to be way out. If you expect it to be 0, then the same with me is negative 7.5. You're way out in the tails. Okay? And then how do you get a confidence interval here? Check this out. Here's our X bar. And here's our range, negative 2.63 to negative 12.36. Okay, so the point of the computer output is to show you that it does align with our manual procedures. Okay, and how to kind of interpret it if you were to see it on a recitation. I guess tomorrow is your recitation. So there's that component. Let me go back. So I guess the question could be, on Tuesday, would you need to do it by hand or read off an output? One question, I can't give you specifics, but be prepared to do it by hand. And then also be prepared to interpret an output if I give it to you. Let's go back to some fudging. Okay, so let's go back here, right? So this guy is a positive 7, okay? So what we're going to do is make that 84, and now we're good, right? Okay, and then more fudging. This guy is 9, so we'll make this 80, and that should take care of that one. So that's my way of hand waving that issue. Now, don't leave, right? Because we're going to wrap up 18 here. And now you may say, please don't put chapter 19 on there. All right, but it is a homework problem. So I do want to talk about that briefly. And my Camtasia work is a work in progress, so to speak. So be patient with that. But for the sake of time, I'm not going to go into PowerPoint. That tends to makes me go a little slower. But I will go into chapter 19 notes, and these are posted. So I just please indulge me with a few minutes, probably till 8:57. And again, I know you guys got to go, so you got to do what you have to do. But let's just talk through these a little bit. All right, so in chapter 19, you have 2 samples that we're worried about here, and I'll double check. I'll go over this again on Tuesday. So on Tuesday, we'll cover chapter 19 a little bit and do some more talking about the exam, but I want to kind of get through this now. So what we're doing, well, in chapter 18, we did so-called matched pairs, and you have a situation where you have before and after measurements are concerned, right? So before a relaxation program, after a relaxation program, those things are in place. So who has Katy Perry on their iPod? Guys, raise your hand too. Yes? Way to go. He's like, oh yeah. Roar, right? So anyway, if you take a random sample of people who went to concerts in 2008 and then compare it to the prices in 2013, you might think that her ticket prices will go up because her fame has gone up big time in the last 5 years. So you can maybe get away with a pair T situation where you would look at like maybe like mu of 2008 or 2013 minus the mean for 2008, right? And then maybe you'll even say that that's probably greater than. And so then I have this comment down here that says, well, you can get away with one column of differences for that situation, but what about this? Okay, I'm old school, but not this old. All right, suppose you have a random sample of ticket prices for Rolling Stones, right? And you have a random sample for Coldplay. You might have different groups of people going to those concerts. And so the question now is, are these samples more likely to be independent or dependent? Again, with the Katy Perry example, the same folks went to the concert in 08 and 13. Here you have different groups, so I'm going to say that this is going to be independent. And then when you have independent samples, now you look at the difference of the two variables. And so chapter 19 focused on the differences in two populations. Coldplay population, Rolling Stone population, that sort of thing. It's no longer the same people with two treatments. We're looking at two different groups altogether and how their differences are assessed. So tune in on Tuesday. We'll wrap this up and talk about the exam. Happy studying. Thank you for your time. It's 8:57.